So what was in page 1 and 2? Remember now? Page 1 and 2 of the chapter was a dot product, right? Was a dot product. And for example, dot product on R3, correct? And you learn this dot product in calculus 3 probably in there. So what this dot product doing in calc 3 is, for example, if I have b dot w, remember this was absolute length of b times the length of w. Remember what is going in here? If this is two vectors sitting inside the three-dimensional space, dot product is simple. How simple is it to calculate the dot product, right? If I give you two vectors. But this has this important information. This is called cosine theta. What is theta? There's vector v, there's a vector w hovering inside the three-dimensional space. They make a triangle, right? Connecting that angle theta was there. All right? This simple algebraic gadget happened to capture amazingly important geometric information about the vectors. Length of the vectors and angle between those two vectors. So they use this. Wow, this algebra is still there in abstract vector space. Can we use this gadget to define geometry? Now I enter endomorphism V. This is not a column vector space, right? All we know is vector space structure, and I just introduced algebra structure, endomorphism algebra, right? If I choose a vector, let me use a P. So vividly, letting you know that this is abstract vectors. It's like a polynomial, right? Polynomial in there. Can we treat it like it is a point in the three-dimensional space so that it has a length? If I have two vectors, position vector, you have its angle, things like that. So there's no geometry in here, and they want to put geometry in there, right? So this was the entrance of non-Euclidean geometry. This is the language of general relativity and all modern mathematics. There is something that we see in there. We want to put geometry so we can visualize this actual world, and that's what they're doing. All right. So again, dot product is very algebraic. Can we define things like this with an abstract vector space so that we can define cosine theta? Nonsense, but we define it. Angle between the two vectors. And that's the inner product. So they begin to capture what kind of property dot product has, and they have this positivity, right? Who remembers positivity of the inner product space? Inner product is denoted like this, V and W, right? This vector space V. We have two vectors. If we want to multiply like this, right? Multiply like this, it becomes, what kind of entity is this? Is that a vector? After you multiply dot product, it becomes a scalar, right? It becomes a scalar. So it becomes a scalar of this own vector. And we're going to limit ourselves in inner product space where this one is really geometric context. Therefore, it has to be R or C. You can't put finite field. No one has yet discovered nice geometry on that. There are different approaches to that. It gets really hard. But if your scalar is a real number or a complex number, then this will serve you as putting the geometry to it. So after you do this, two vector, like a dot product, then it gives you a number, a scalar in there. What kind of property will capture this dot product was that if you do it to itself, what was it? What happened if you dot it to itself? Greater than or equal to 0, right? So that property, and what was the next one? Was that definiteness or something? Yeah, definiteness. And if that one is a 0, that means V was a 0, and V is a 0, then inner product to itself is a 0. Again, we don't use dot product anymore. That's only reserved for column vector space. And we want to extend this dot product kind of thing in here so that we can, once we have something like this, we're going to define this cosine theta. And there was some linearity in there. This is called multilinearity. It says linearity in the first slot or something like that. What was that? If I have two vectors, v1 and v2, this becomes, if I remember this, v1w plus v2w, right? I think you have seen something like this. This is called multilinearity, and you've seen that in the determinant map. So here is an example. If it is a square matrix, how would you understand this one? Does it look like a square with one column and second column? So W is a column vector. And this first column vector is actually sum of two column vectors. But it's just column vectors, right? And I put the determinant in there. Alright? This is called the multilinear property of a determinant map. It actually becomes determinant of v1 w. See what happens? Plus determinant of v2 w. You can experiment it yourself. You write down 2 by 2 matrix and split your first column into sum of two vectors. And then calculate these two determinants separately and add them together, and it's exactly the same thing. This is called multilinear property. If it is larger side, this principle holds. In fact, playing with this principle, you can deduce the formula of everything about determinant. This is the governing principle of a determinant map. All right? So you've already seen this type of thing, right? Doesn't it look just like that? But determinant does not have a positive property or definite property, but it has nice, very nice linearity property. This bracket is just like this one. Try to relate to something that you've probably already seen. Does that make sense? Not only for column, this works for rows as well. You look at the rows, split into two rows, sum of two rows, and this determinant becomes the positiveness. Positive, the sum of these two things. All right? So, let me challenge you a little bit in here with the following. If I have determinant of v1, I want you to do this in your mind and see what happens. Then it'll help you to understand this linearity and the weird terms. So, can you split this one? One at a time, right? You're going to treat this one as a W, correct? And then split this one first. Do this in your mind. And then do things one at a time. So, let's see. Who wants to go for simplest part in here? Who wants to go for V1? V1, W1, thank you. Right? Do you see the second one? V1, W2. V2 goes to W1, determinant. V2, W2, right? If you do one at a time, it's just like multiplying V1 plus V2, whatever the multiplication, crazy multiplication I defined, is like this. As if it is just a usual algebraic structure. Can we swap these two? And whatever you want? That was a skew property, right? Whenever you swap the two rows in a column, the sign of the determinant changes, right? You can't do that, but just the sign change, so it gives you a lot of that sign change is the built-on to plus minus thing. When you calculate the determinant of 4 by 4 by hand, you go through plus minus thing, right? That is because of this skew property, and you can show one at a time. All right, so that's kind of linearity that's involved in there. So let me challenge you to here. If I have something like this, do you think you can unfold this one? This is inner product, right? We don't know anything about this inner product. All we know is this linearity. Not even in the first slot, it's also in the second slot as well, if it is over the real. If it is over the real. It expands exactly like that, right? So what is it? V1, W1, V1, W2, V2, W1, V2, W2, right? If it is over the real coefficient, if you swap these two, the sign doesn't change. If it is over the complex, if you swap it, you have to conjugate it, things like that. But that's the linearity. I want you to, rather than just staying like this, I give you a little feel about what the linearity is doing. Whenever linearity, you can kind of unfold complicated expression to some of these things like that. And there was a scalar property as well, right? What's that? A goes outside, like that, right? Again, if A isn't over here, and if it's complex, then you have to do this weird business of complex conjugate. The reason they had to do the conjugate is to preserve this positiveness. So I'm going to give you an example, because I already read all that. But here's an example not given by the polynomial. The best example is R3. So watch out here. R3 already has a dot product, right? I'm going to mess with that. So the new inner product structure is given by following 1 and 2 and 3, 0, 0, 0, 0, 0, 0. There's a diagonal matrix again. The significance of diagonal matrices come in play here. B1, B2, B3. This is a row vector, A1, A2, A3. All right, I'm going to do the multiplication in here, right? I'm going to do the multiplication, but this is my definition, going backward, column vector A1, A2, A3, B1, B2, B3. This has nicely built-in dot product already, right? I'm messing with it, defining a new inner product. Different example than what you did in the test problem. This is a definition, okay? So I'm going to show you. We're going to multiply. What happened if it is multiplied like this? Let's multiply this one first. You see that? That was a column vector. What is it? B1, 2B2, 3B3, right? If you multiply these two, you further multiply it, what do you get? A1, B1, right? 2 times A2, B2, and 3 times A3, B3. All right? Okay. So that's the definition. If I have two column vectors, you define it like this as an inner product space. Inner product like this. Now you check if it's a positive. Check if it's a definite. If the linearity holds. Linearity will hold in the first slot. All that. All right? Let's see positivity. If these two vectors are equal, what's going to happen? A1 squared, right? 2 times A2 squared, 3 times A3 squared, right? So do you see that this is a dot product with a little tweak of a coefficient? If these were 1, 1, isn't that the dot product, same old dot product again, right? But I scaled a little bit and happened to still satisfy the nice property of inner product they wanted to capture, and so that they can put out the geometry in sensible way. Well, when this is 0, well, this is always a positive, is that right? Why is that? Because you think the A1 squared is a positive, right? But it's not. Actually it is, because it's a real number, right? But you can see this whole thing is going to be messed up if this is a C3, right? Therefore, it has to be some conjugates involved so that we pull out absolute value of anything. That's why there's a conjugate involved. If it is just leave it like this without conjugate, it's going to hit negative number when you do that. So it's already positive, because positive, positive, positive. And when it's a 0, well, this got to be all 0. So that makes A1, A2, A3 0, things like that, right? So linearity is relatively easier to show. But these are the positive definitions. So do you see that? You can change these numbers to anything you want, right? As long as they're positive, correct? If I change this to -2, you can see that's not going to be good, right? So the more complicated version of this one. So if I give you really this one only interact between the first entries, between second entry and third entries, right? But you can still write down all the entries. They're all interacting each other, and that matrix will be really messy. Yeah, go ahead. so that it end up at positive greater than or equal to 0. That's the positivity property, and so on. All right? All right, so you can put more numbers here. You see that? Then they're all going to be mixed each other. It's a big question. How are we going to determine this positivity? If they're all mingled each other. There's no zeros here, right? I'm going to put 5, 6, 7 and negative and all that. And then you have just long, like 9 terms, right? They're all multiplied each other. The positivity becomes a big problem. Do you see that? This completing square is going to be really messy. And what they do is they choose a different basis and diagonalize it. That was the whole point of diagonalizing business. That was the whole point. Let me say that 3 more times. That was the whole point of the business of diagonalizing, because they're looking at this nice inner product structure rising from the nature, and you want to see how this one really looks like, and you want to diagonalize like this and clearly see what the geometric structure of you looking at it there is. This structure is the first page of the special relativity. If you look up the first page of a special relativity or Einstein theory, they're introducing this structure. Here's x, y, z, and here's a time spatial, and here is the hyperbolic measure, and then that's exactly this one. Only weird thing is that there's a negative 4 times something. That becomes a semi-Riemannian structure. This thing is never be an interest to mathematician. They want it positive, and Einstein noticed that it's got to be negative. That's the nature works. Then we have to rewrite this entire thing with this negative. It's called semi-Riemannian geometry. All right. So diagonal business is important, and Einstein was doing this. This whatever the coordinate system and this matrix becomes really messy, and he wanted to see that, and canonically that still works no matter what base you choose. Things like that. That's the most important business of diagonalizing. All right? So if I write down this type of 2 things multiplied called quadratic form. Quadratic form. If I write down complicated quadratic form, then there is a matrix always that makes this one into this form. But these are non-zero. They're not diagonal. They want to look at right angle. Boom, there is this right angle to C such that that quadratic form representing this inner product structure becomes diagonal. When it's a diagonal, things are clear. This is like perfect.